Okay, so in this set, what we're going to do is we want to find the slope, not the slope, we want to find the directional field for this differential equation, right? And what do we see here in this case? Is we have this useful piece of information. Is dy dx a function of x only, or is dy dx a function of y only? So, note, I did literally just pull this off the internet to search up how to match slope fields with differential equations. You can get the exact same thing. Okay, instead of trying to graph everything out, just search up these like tricks. Okay, so we see that the parallel slope within the same row. Okay, so what does that mean? Okay, I'm just going to tell you guys right now, I actually do know the answer here. It is this one. But I'm going to explain it to you guys in a second. I want you guys to think about this. Look. If dy dx is a function of y only, then we see that the parallel slopes within the same row. So, parallel slopes. Like, again, what is the slopes that you see here, right? These are all slopes. I mean, they are, okay? Then they said that the parallel ones are in the same row. Again, what is a row? A row is like this, right? Horizontal. So we see that one there, and that's it there. There you go. That's all it was. I'm not even kidding. Like, guys, let's identify that. Look at this differential equation. It says y prime. Sometimes you may need to isolate for y prime, but y prime is the slope, and then it says that its slope is purely a function of y. Then that denotes that, look at this. We see this is what it means. We have these parallel horizontal lines. That's all it was. Okay, for this next one, why is my screen frozen? Okay, for this next one, we see that we want to find the limit of y. And note that y of 0 is equal to 2. So I'm going to plot that point y of 0 is equal to 2. So basically where x is equal to 0, okay, where x is equal to 0, right here, right? Where y is equal to 2, right here. Well, then it says, as x goes to infinity. So, as x goes to, what is that, guys? Like, look right below it. Right here. You have the line right here. You have it. That's also where x is equal to 0. Right? So it satisfies the x location. And then it says that it's going to infinity. Like if you look at these lines, look, it's like curved, 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 and it's getting less curved and less curved and less curved. Right? So in other words, we see that this line right here, and that line is y equals 1. Okay, so it's this graphical interpretation, which could be kind of tricky, but you should try to make sense of using this initial condition and then using this fact right here that this line is a straight line and it is going to x as x goes to infinity. So then you see that where that line is. So we say the limit as x goes to infinity for y is the same thing as the limit. I'm just going to write. It's 1. There it is. That's all it is, guys. It's kind of hard, actually, because it's like that there's not much going on, so you would think that there's more. But that's it. Okay. Now for the part that I actually like doing is solving this differential equation. Okay. I'll rewrite it again. R prime y 1 minus y. So note that this is just separable because I don't see any x's here, so we can really just and I'll rewrite the separable way real quick. Dy dx. That's all you gotta do. Just write y prime as dy dx, and you can see what do. We literally just go dy. y1 minus y. Put the dx on the other side. Let me put an integral sign by x. And then what do we see? We see x, c, is equal to this integral. Okay. Yeah, sorry, I almost jumped a step here. Okay, so y, 1 minus y. actually delete that integral real quick. So 1 over y, 1 minus y. What you need to do is you need to do partial fraction decomposition. That's the only way you're going to solve this one. There's not a substitution here. Okay. So note, just write it as a for y plus b over 1 minus y. And then if you multiply both of these guys by this over here, you get 1. So multiply everything by this over here, okay? So you get 1, then you get a over y, and then multiplying by 1 minus y. Those go away. You get b, 1 minus y, 1 minus y. So usually I skip a lot of steps here, but I'm not going to do it for you guys. So a, 1 minus y, plus by. And that's what you can do. You can say if, I promise you can do this. Just say, look, if y is equal to 1, then when you get 1 is equal to, okay, if y is equal to 1, then, look, then it's a multiplied by 0. So it's just 0 plus b is equal to 1. And then you could just say, if y is equal to 0, yes, I'm literally just picking random numbers, but it's not so random that you can pick numbers that help your case. Then we get 1 is equal to what? A plus 0, a is equal to 1. So the fraction decomposition of this guy turns into what? I believe it's both 1s, yeah. 1 over y plus 1 over 1 minus y. That's it. Nice little fraction decomposition here. So now let's go back here. Now we can rewrite this integral. So we have two integrals, 1 over y, dy, plus 1 over 1 minus y, dy, which is equal to ln of y plus ln of 1 minus y. And what you can do, since these are, just leave it like that, okay? So you get x plus c. Yeah, we just want to solve the differential equation. So you can just leave it, literally just like this. Just leave it there. Now, whatever. When you have two natural logs plus each other, you can multiply them. They're products, they're inner products. So there you go. You can leave your answer like this. This is perfectly fine. You don't need to solve for y. There's no point. It's an implicit solution. There you go.